Voyager 1 is the fastest, farthest traveling object humanity has ever built. It's been flying for almost 49 years, moving at roughly 38,000 miles an hour, and it has now put more distance between itself and Earth than any human-made object in history. At that speed, on its current trajectory, it would take Voyager 1 about 73,000 years to reach the nearest star system beyond our own. 73,000 years to cross a gap that, on a map of the galaxy, barely registers as a rounding error. That's not a temporary limitation waiting on better engines. That's the actual physical shape of the problem. And it's the reason so many serious scientists, working on this exact question right now, keep arriving at some version of the same uncomfortable conclusion. This isn't a story about giving up on the idea. Real, funded, peer-reviewed research into interstellar travel is happening today in 2026, spread across universities, private foundations, and government-funded labs on multiple continents. And some of it is genuinely promising, drawing on physics, material science, and propulsion engineering, all advancing steadily, even when no single headline captures the cumulative progress. But the honest version of this story, the one grounded in actual physics and actual published research, rather than science fiction optimism, explains exactly why crossing interstellar space remains, for now, arguably, the hardest engineering problem humanity has ever attempted to solve. Harder, in a very real sense, than anything the Apollo program or the International Space Station ever had to overcome, because those problems were merely difficult, while this one keeps circling back to constraints written directly into the laws of physics themselves, and why some of the smartest people working on it have started using words like on hold, and more bluntly, nowhere, to describe where we currently stand. Let's start with the scale of the problem, because everything else follows from it. The nearest star system to our own, Alpha Centauri, sits about 4.24 light years away, roughly 25 trillion miles. To put that in a scale a human mind can actually hold on to. If you shrank the distance from the Earth to the Sun down to 1 inch, Alpha Centauri would still be more than 4 miles away on that same scale. Or think of it this way. Light itself, the fastest thing in the universe, the thing every velocity in physics gets measured against, still takes over 4 years just to make that one-way trip. Nothing built out of matter has ever traveled anywhere close to that fast, and nothing built out of matter, under our current understanding of physics, ever will. Our fastest spacecraft, the kind that took humanity to the moon and past every planet in the solar system, are simply not built to operate at the speed such a crossing would demand in any reasonable amount of time. Here's where the actual physics starts working against us, and it starts with something called the rocket equation, first properly formalized by Russian scientist Konstantin Tsiolkovsky back in 1903. Decades before humanity had built anything capable of leaving the ground. In plain terms, it describes a brutal, unavoidable trade-off. The faster you want your spacecraft to eventually travel, the more fuel you need to carry to get it there. But that extra fuel itself has mass, which means you need even more fuel just to accelerate the fuel you're carrying. The relationship isn't linear, it's exponential. Push your target speed high enough and the fuel requirement doesn't just grow, it explodes mathematically toward the point of complete absurdity. It's the same basic reason a rocket capable of reaching orbit is almost entirely fuel by mass, with the actual payload, the part that does anything useful, making up only a small fraction of the total vehicle. Every additional bit of speed you want costs disproportionately more than the speed increase before it. Concretely, using the most efficient chemical rockets humanity has ever built, accelerating a spacecraft to even a modest fraction of the speed needed for a reasonable interstellar crossing would require a fuel tank many, many times larger than the spacecraft itself, and that's before accounting for the fact that you'd eventually need to decelerate at the other end too, which, under the same equation, roughly squares the problem all over again. Chemical rockets, in other words, aren't just inefficient for this job. They are, mathematically, disqualified from it entirely. For any campaign expected to arrive within a human lifetime, that's not an opinion. That's what the equation says, and it's the same equation every rocket engineer on Earth has to work within, whether they're launching a satellite or dreaming about Alpha Centauri. So serious researchers, going back decades, have looked past chemical rockets entirely, towards stranger, more exotic propulsion ideas. And this is where the real, current, ongoing research picks up. The most well-funded, most publicly visible of these efforts is Breakthrough Starshot, announced in April 2016 by physicist Yuri Milner's Breakthrough Initiatives. With backing and public support from figures including the late Stephen Hawking, the concept, at least on paper, sidesteps the rocket equation entirely. Instead of carrying fuel on board, you build an enormous array of ground-based lasers and use them to push a fleet of tiny, ultra-thin light sails, each one carrying a computer chip, smaller than a fingernail, together weighing barely a gram, up to roughly 20% of the speed of light. At that speed, a probe could theoretically reach Alpha Centauri in about 20 years, rather than tens of thousands. It's an audacious idea, and when it was announced, It captured public imagination precisely because it seemed to offer a genuine, physics-respecting shortcut past the rocket equation's brutal math. Here's where the honest, current state of that project actually stands, as of 2026, and it's more complicated and more instructive than a simple yes or no. At Starshot's founding, the team identified somewhere between 25 and 30 major, potentially mission-ending technical hurdles that would need real solutions before any probe could actually launch. Building lasers powerful enough, cheap enough, and precisely coordinated enough to focus a beam accurately across enormous distances. Building a sail material light and reflective enough to survive that beam without vaporizing. Protecting a probe traveling at a fifth of the speed of light from being shredded by even microscopic dust grains along the way. And figuring out how to send any data at all back from a probe 4 light years away using a transmitter the size of a postage stamp. 37 separate research groups spent years working through those specific problems, publishing peer-reviewed papers along the way on everything from sail material science to laser array design to the communication challenge of coordinating a swarm of tiny probes across light years, rather than treating the whole endeavor as a single monolithic engineering task. In September 2025, Scientific American ran a cover story on the project bluntly titled, in its published form, How a Billionaire's Plan to Reach Another Star Fell Apart, describing what the article characterized as the quiet demise of the initiative, reporting that the project had effectively stalled, its ambitious 30-year roadmap unmet, key researchers moved on, and momentum lost. The piece drew on interviews with people who had worked directly inside the project during its most active years, giving it real, first-hand reporting weight rather than outside speculation. That reporting reflects a real documented account of where things stood, sourced from people who worked on the project directly. But it isn't the only account. In direct response, published on the Centauri Dreams research blog in early March 2026, longtime interstellar flight researcher Paul Gilster pushed back hard on that framing, arguing the project has not failed and has not been cancelled. That Phase 1 of Starshot achieved exactly what it set out to do, which was to identify the genuine show-stopping obstacles and determine whether credible solutions exist for them, and that the project was deliberately paused in 2024, not abandoned, specifically to restructure and seek broader support before committing to a costlier, longer next phase. Gilster's rebuttal draws on years of his own close coverage of interstellar propulsion research, giving his account real standing as well, rather than treating it as a simple defense of a project he happens to favor. Both of these accounts are grounded in real events. The disagreement isn't really about the facts. It's about how to characterize a research program that spent 9 years doing exactly the kind of unglamorous, incremental, occasionally discouraging work that real breakthrough science requires, without producing a launched spacecraft, and without yet definitively ruling out that it eventually could. By music. And underneath that debate about framing, the actual engineering numbers, published this year, are sobering regardless of which narrative you find more persuasive. A study published in the journal Acta Astronautica in February 2026 directly compared several proposed solar sail missions against our current technological capability. Solar Cruiser, a much more modest, near-term solar sail mission designed to stay within our own solar system, would only need our technology to improve by a factor of roughly 2 to 3 to become achievable, a real, credible near-term target. Breakthrough Starshot, by contrast, according to that same published analysis, requires our engineering capabilities to improve by hundreds of times over across several key areas simultaneously. Laser power, sail material science, miniaturized electronics, and long-distance communication all at once, all needing breakthroughs that don't currently exist even in early laboratory form. That's the real, current, quantified gap between where we are and where an actual interstellar sail mission would need to be. Music. And even if every single one of those engineering hurdles gets solved eventually, Breakthrough Starshot was only ever designed as a one-way flyby mission for a probe smaller than a postage stamp, not a spacecraft capable of carrying people, instruments large enough for detailed science, or any plan to return. Solving Starshot's problems solves a real, specific, narrower question. It doesn't solve the much larger, much harder question of moving anything resembling a crewed mission across that same distance. Music. Which brings us to the harder, more human version of this problem. Even setting propulsion aside entirely, what would actually happen to a spacecraft, and the people or instruments aboard it, during a journey lasting decades or centuries? Music radiation is one of the more underappreciated obstacles here. Beyond the protective bubble of our sun's heliosphere, the same boundary Voyager 1 and Voyager 2 have already crossed into interstellar space, a spacecraft is exposed to a steady bombardment of galactic cosmic rays, high-energy particles, accelerated by distant supernovae over millions of years, that Earth's magnetic field and thick atmosphere normally shield us from almost entirely. For a robotic probe, that radiation gradually degrades electronics over time, a real measurable effect engineers already have to design around for missions far closer to home than interstellar space. It's part of why spacecraft heading beyond Earth's protective magnetic field carry radiation-hardened components specifically built to resist exactly this kind of long-term degradation. For a crewed mission, sustained over years or decades with no planetary magnetic field for protection, that same radiation becomes a serious, unsolved problem for astronaut health, one that current spacecraft shielding technology is nowhere close to fully solving even for multi-year missions to Mars, let alone multi-decade or multi-century voyages far beyond it. NASA's own published research into Mars mission radiation exposure already treats it as one of the central unresolved health risks for a round trip lasting roughly 2 to 3 years. Stretch that same exposure out across a journey measured in decades or centuries instead, without a comparably scaled-up shielding solution, and the health risk compounds well past anything current spacecraft design has a real answer for. Music. Then there's the collision problem. Interstellar space isn't perfectly empty. It contains sparse but real clouds of gas and microscopic dust, remnants from ancient stellar explosions and the slow churn of galactic chemistry, distributed thinly enough that Voyager 1 and Voyager 2 have crossed into it without incident at their comparatively leisurely speeds. At normal spacecraft speeds, this poses essentially no danger. But at any meaningful fraction of the speed of light, the physics changes entirely. A dust grain weighing a fraction of a gram, hit at 20% of light speed, carries kinetic energy comparable to a small explosive impact, simply because kinetic energy scales with the square of velocity, double your speed, and the energy of any given collision doesn't double, it quadruples, which is exactly why relativistic speeds turn even sand grain-sized debris into a genuine structural threat, rather than a minor annoyance. Breakthrough Starshot's own team has argued this risk is manageable for something as small and thin as their proposed sails, protected by a relatively light coating. A genuinely researched, published position, not a handwave, and one that's specific to a probe with almost no cross-sectional area and no fragile human occupants to protect. But scale that same physics up to a spacecraft large enough to carry human beings, months or years of supplies, the kind of shielding a crew would actually need to survive radiation exposure too. And the collision risk scales up right alongside it, in ways nobody has published a credible, complete engineering solution for yet. Music. And then there's simply time itself, which turns out to be its own kind of obstacle, separate from the engineering. Even at Breakthrough Starshot's optimistic target of 20% of light speed, a speed no human-scale spacecraft has ever come remotely close to reaching, a one-way crossing to Alpha Centauri still takes about 20 years, followed by another 4 years, and change just for a radio signal to confirm arrival and send back whatever data the tiny probe managed to collect during its brief, high-speed flyby. For any mission slower than that, which is to say essentially every propulsion concept currently past the laboratory theory stage, the timeline stretches into centuries. That forces an uncomfortable question for any crude version of this idea. Do you send a small crew designed to live out their entire lives aboard a ship, hoping their descendants, born and raised entirely in transit, finish the journey generations later? Researchers who've studied so-called generation ship concepts seriously have flagged genuine, unresolved problems well beyond the propulsion question. Maintaining a genetically viable, healthy population across dozens of generations, confined to a single closed environment, preserving enough cultural and technical knowledge across centuries that the ship's eventual arrivals still remember why they're there and how to actually operate the systems, keeping them alive, and sustaining a stable, functioning society for that same span of time without the option of leaving, resupplying, or turning back. None of those are propulsion problems. All of them are just as unsolved as the propulsion problem is. Music. Or do you attempt some form of long-term biological stasis, hibernation, or suspended animation instead? Technology that, as of 2026, exists only in early limited research on other animals, with nothing close to a proven, safe method for suspending human biology for years or decades at a time. Some medical researchers have made real, incremental progress, inducing torpor-like states in small mammals under laboratory conditions. And NASA has funded early-stage studies into human torpor, specifically for shorter Mars mission timescales. But scaling that from a lab experiment lasting days or weeks up to a safe, reversible, multi-decade human hibernation remains, honestly, closer to science fiction than to funded, near-term engineering right now. Neither option is close to solved. Both raise problems that go well beyond propulsion and into unresolved questions of biology, psychology, and multi-generational social stability that no engineering breakthrough alone can fix. Music. It's worth addressing the two ideas that show up constantly in popular science fiction and popular science coverage alike, because both of them turn out to run into exactly the same wall, just from different directions. On music, The first is the Alcubierre warp drive, a real published piece of theoretical physics proposed by Mexican physicist Miguel Alcubierre in 1994, working directly within the mathematics of Einstein's general relativity rather than against it. The idea, in simplified form, is elegant. Rather than moving a spacecraft through space at high speed, you instead contract space itself in front of the ship and expand it behind, riding inside a kind of bubble of flat, undistorted space, while the space around that bubble does the actual moving. Because the ship itself never technically exceeds the speed of light relative to the space immediately around it, the idea doesn't outright violate relativity's speed limit. It works around it, in a way general relativity's equations technically permit. That's exactly why it captured serious physicists' attention in the first place, and why it still shows up in genuine academic papers today. Music. The catch, and it's a serious one, is what the mathematics requires to actually build that bubble, a form of matter with negative energy density, sometimes called exotic matter, that would need to warp space-time in exactly the opposite way ordinary matter does. As of 2026, no experiment has ever detected a substance with the specific properties that solution requires, and there's no confirmed physical mechanism for producing or containing it, even in principle. Some theoretical work has suggested the energy requirements might be lower than early estimates once assumed, but lower than absurd and achievable remain very different categories, and nobody working in this field claims otherwise. The warp drive isn't ruled impossible by the mathematics. It's ruled impossible for now by the complete absence of the one physical ingredient the mathematics depends on entirely: music. The second recurring idea is antimatter propulsion, which sidesteps the warp drive problem by relying on physics we've already directly observed and produced in laboratories, rather than a hypothetical form of matter nobody has ever detected. When matter meets its antimatter counterpart, the two annihilate completely, converting their entire mass directly into energy, by far the most efficient reaction physics allows, dramatically outperforming even fusion. In theory, a small amount of antimatter fuel could deliver an enormous amount of thrust. In practice, humanity's particle accelerators currently produce antimatter in quantities measured in billionths of a gram, at a cost running into the trillions of dollars per gram by some published estimates, and no proven method exists for storing meaningful quantities of it safely for any extended length of time, since it destroys any ordinary matter container it touches on contact. The physics of antimatter propulsion is sound. The production and storage engineering behind it isn't just difficult, it's, as of right now, essentially non-existent at any scale remotely useful for propulsion. Music. There is one genuinely different approach worth taking seriously, because it doesn't rely on speed at all. Einstein's own relativity actually offers something like a loophole, at least in theory. As an object's speed approaches the speed of light, time for the people aboard that object slows down relative to time back on Earth. A real, experimentally confirmed effect, not science fiction. Push a spacecraft close enough to light speed, and a crew could, in principle, experience a journey of just a few years aboard ship, even while decades or centuries pass back home. It's a genuine escape hatch from the raw distance problem, at least from the traveler's own point of view. But that loophole comes wrapped in a catch that circles right back to where this all started. Reaching a speed anywhere close enough to light for that effect to matter meaningfully requires an amount of energy that dwarfs anything remotely achievable with current or foreseeable propulsion technology, chemical, nuclear, or laser-driven alike. Relativity doesn't get you out of the energy problem. It just moves the finish line further out while making the price of reaching it even steeper. Music. Nuclear propulsion concepts, including fusion-based designs, studied seriously by projects like the British Interplanetary Society's Project Daedalus back in the 1970s and its modern successor studies, offer real, calculated improvements over chemical rockets, potentially reaching speeds of 10 to 12% of light speed, using fusion reactions rather than chemical combustion. That's genuinely significant progress on paper, roughly halving the 20-year Alpha Centauri crossing time starshot targets, without needing anything as exotic as a beam of ground-based lasers focused across light years of empty space. It's also propulsion technology that, decades after being proposed, still exists only as engineering studies and simulations, because humanity has not yet achieved sustained, controllable nuclear fusion here on Earth in the first place, let alone miniaturized and weaponized it, in the literal engineering sense, into a working spacecraft engine. Even the most optimistic recent fusion energy milestones, ignition experiments achieving net energy gain for a tiny fraction of a second inside a lab, a real and celebrated achievement in its own right, remain a very long way from a sustained, controllable reaction stable enough to power a multi-year spacecraft journey. Every proposed shortcut past the rocket equation, it turns out, runs into some other fundamental barrier almost immediately behind it: music. So where does that actually leave the honest answer to a title like this one? Not at "it's impossible," full stop, forever. That's a stronger claim than the current evidence actually supports. And serious researchers working on this problem right now would be the first to push back on that framing, the same way Centauri Dreams pushed back on Scientific American's characterization of Starshot. What the evidence does support is considerably more sobering than most popular coverage of interstellar travel lets on. With every propulsion technology that exists today, or that exists as a credible, physics-respecting engineering study rather than pure speculation, crossing interstellar distances within a single human lifetime remains firmly out of reach. Not difficult in the way a hard engineering project is difficult. Difficult in the way that requires multiple, simultaneous, currently non-existent breakthroughs in propulsion, materials, science, radiation shielding, and, for any crewed mission, human biology itself arriving together on top of each other before any of this becomes remotely feasible. Or music. It's worth being precise about what will never leave the solar system would actually have to mean for it to be true, because the strong version of that claim is almost certainly wrong, even if the weaker, more honest version holds up uncomfortably well. Robotic probes, similar in spirit to Voyager but purpose-built for the crossing, are very plausibly within reach within this century if even a fraction of Starshot's original goals eventually pan out, restructured phase or not. What looks genuinely, currently out of reach isn't leaving the solar system in any form. It's doing so with a crewed mission, arriving within a time frame any currently living person, or their direct descendants for many generations, would ever see completed. Those are two very different claims, and conflating them is exactly the kind of exaggeration this channel has tried to avoid across every one of these videos. Music. That doesn't mean the research is pointless, and it doesn't mean nobody is trying. It means the honest timeline for interstellar travel isn't measured in years or even single decades of engineering effort. It's measured in the accumulation of separate fundamental scientific breakthroughs, each one uncertain, each one currently unscheduled, stacking on top of each other before a realistic mission profile even starts to take shape. Paul Gilster's own defense of Starshot makes exactly this point. Identifying the real obstacles clearly, rather than pretending an easy answer exists, is itself the necessary, unglamorous first step of any serious multi-generational research program, whether that program ultimately succeeds or not. Progress in science doesn't always look like a launch. Sometimes it looks exactly like what Starshot's phase when actually produced. A precise, honest list of everything standing in the way, verified rather than guessed at, which is a real form of progress, even when it doesn't come with a rocket on a launch pad. Music, Voyager. One, still out there right now, still transmitting, still the fastest and farthest thing humanity has ever built, remains a genuinely humbling benchmark for exactly this reason. Built in the 1970s, running on power supplies that decay a little further every single year, still working today, and still roughly 73,000 years away from even our nearest stellar neighbor, on a trajectory that happens to be aimed nowhere close to any star system in particular anyway. Everything since, Breakthrough Starshot, fusion propulsion studies, relativistic time dilation calculations, antimatter research, and the theoretical mathematics of warp geometry, represents real, serious, funded attempts to shrink that 73,000-year number down to something a human lifetime, or a few generations, could actually survive. As of 2026, none of them have gotten there yet. Some of them, honestly, may never quite get there. But the gap between we haven't solved it yet and will never leave the solar system is exactly the gap this entire field of research is currently living inside, and it's worth understanding the real reasons why, rather than either dismissing the dream outright or pretending the physics is easier than it actually is. Music. So, where do you land? Genuinely impossible with anything resembling known physics, or just a problem that needs more time and a few more breakthroughs than most people assume? Tell me in the comments, and if you want to be here for whatever comes out of Breakthrough Starshot's next restructured phase, or the next fusion propulsion milestone, or the next serious paper on exotic matter and warp geometry, subscribe, because this is exactly the kind of slow-moving, decades-spanning story that's easy to miss unless you're actually watching for the real updates as they come, rather than the headlines that oversimplify them in either direction, either declaring the dream dead the moment a project pauses to regroup, or promising a warp drive is right around the corner the moment a new paper gets published. The truth, as usual, sits in the much slower, much less dramatic middle, and that middle is exactly where the real research is actually happening right now.